So today we're going to briefly talk about a bunch of other Greek mathematicians that we don't have time to cover fully because after the exam, I would like to start talking about some other ancient civilizations and then move on to at least a few of the more modern topics. There's actually so much in the ancient Greek world that you could have a whole course that's just on this. So basically today we're going to cover Apollonius, Eratosthenes, Aristarchus, etc. So there's actually a few more after that, and these are all going to be brief. So let's begin with Apollonius of Perga. So he was born in Perga, which would be in modern day Turkey. That was about 262 BCE. And then he worked in Alexandria, and so presumably that's where he died, and that was around 190 BCE. So he's actually done quite a lot of works. For example, conic sections. So his work on the conic sections was very influential. Cutting off of a ratio. There's some lost works, including methods of fast calculations. So, what are quick ways to do certain, arithmetic operations? But also including calculation of pi. So a lot of times we know that these mathematicians did these works because other ancient mathematicians refer to them, but the actual works have been lost. So his work also included what today we would consider to be quadratic equations. And remember that the ancient Greeks did not use algebraic notation the way we do. That's a relatively modern invention. He made use of what's called application of area. So we saw application of area, and then here was the construction, what the image looked like. So you start with a rectangle that has dimensions A, B, and then you get a rectangle of area A times B. And then remember we said, let this be 1 unit. So this height here is 1. And so when we complete this construction, this rectangle has the same area as this one. If the height is 1 and the area is A times B, then this length must be A times B. So, and this is the reason why this construction is called application of area, because it converts an area into a length. So an area into a length. Now, Apollonius also did astronomy, and he used something called the epicycle model. So it's a little bit complicated. So here's the Earth. And now the thing is, if you actually study the motion of planets, you'll discover that these planets don't move in a perfect circle around the Earth. And so he came up with a a different way of viewing it. So a different way of explaining why it's not a perfect circle around the Earth. So he imagines that there's a circle around the Earth. There's a point C on the circle that is moving around the Earth. And at the same time, the planet is moving in a circle around this point C. So this point is moving around the circle, and then P is rotating around that circle wherever that circle happens to be. And so that's how he explains planetary motion. His work on the conics consisted of a total of 8 books. So again, we know that there were 8 books because of ancient writers, but only 7 of these books survive. So books 1 through 4 were his introduction to the conics, and he starts with a cone. So basically he constructs a conic by literally cutting through a cone. Now, these first 4 books exist in the original Greek. However, books 5 through 7 only exist in Arabic. So the books were copied, eventually copied into Arabic, and we'll learn a little bit more about that later, about why, and why the Arabic version actually continues to exist. And here, for example, is just one of the pages of the Arabic version of the book. Now, Apollonius did not write the first book on conics. There were earlier mathematicians who also studied conics. So for example, Menachmus. And remember that Menachmus used conics to duplicate the cube. Archimedes, and also Euclid. So Euclid wrote a book on the conics. And so conics were used earlier to duplicate a cube and to trisect an angle. Now, we know that the ancient Greeks viewed conic sections as literally sections, meaning cut of a conic. And so the sect part of section does actually mean cut. So for example, if you think of the word dissect, it means to cut. So conics were viewed by cutting cones, but previously they made their cuts perpendicular to, like, so if you look at one of the lines of the exterior of the cone and then cut with a plane that's perpendicular to that line. And so in this illustration, by making this cut that's perpendicular to one of the lines on the outside edge of the cone, it looks like we get an ellipse. Well, if that's the case, how do you get the other conics? So here in this example, we got an ellipse, but how would you get a parabola out of this? If I try moving my cut a little bit further down, I'm just going to get a bigger ellipse. Then I move even further down and I get just a bigger ellipse. So I cannot seem to get all of the conics from cutting this cone using a plane that's going to be perpendicular to the side. So let's see what they did before Apollonius, and then we're going to see how that changed with Apollonius. So if you make a cone where the angle at the top is less than 90 degrees, and then you make a cut that's perpendicular to the side, that's going to give you an ellipse. If this is exactly 90 degrees, and then you make a cut that is perpendicular to the side, then this cut is actually parallel to this. This cut only intersects the cone. It just goes straight parallel to this line the whole way down, and that's going to give you a parabola. But if this angle is greater than 90 degrees, you're going to cut perpendicular to that side, and that's going to give you a hyperbola. So for example, this is how Menaechmus would have actually done it. So let's see what Apollonius did that was different. So first thing is, the cone need not be a right cone. Now, in a right cone, if you drop a height, so this is going to be a line that's going to be perpendicular to the base, it's going to hit the base right in the center. So basically, the vertex of the cone is lined up like perfectly centered over the base. So that's a right cone. But if it's not a right cone, when you drop that perpendicular line down to the base, it's going to hit someplace other than the center of the base. So a cone that's not right is called oblique. So basically, the cone is kind of slanted, and that's what we mean by that. Now, the next thing that Apollonius did is he replaced the single cone with the double cone. Finally, he showed that you can choose any double cone at all. It can be a right cone or it could be an oblique cone, so it could be slanted or not. And then instead of always making the cut perpendicular to the side of the cone, what you're going to do is you're going to vary the angle of the cut. So for example, here, if you make the cut at this angle, you're going to get an ellipse. Now this cut here is actually parallel to this line here. So these two lines are parallel. And if you do that, you're going to get a parabola. Finally, here's a cut that's going to be a little bit more vertical, and it's going to cut through both the top and the bottom of the cone. Notice that with the parabola, because this line is parallel to this line, the cut here will only intersect this part of the cone, and it'll never intersect the top part of the cone because the lines are parallel, they'll never meet. But with a steeper cut, the cut's going to intersect both the bottom and the top of the cone, and that's going to give you the two branches that you see on a typical hyperbola. So that's how Apollonius viewed conic sections. Now, Apollonius probably introduced the following two terms: ellipse and hyperbola. And then he used the word parabola. Now, the word hyperbola and parabola share a common part. The bola, that means throne. So this is thrown beyond, and this is thrown alongside. So alongside and then beyond. So anyway, so it's not exactly clear why the thrown beyond made sense to him, but that's the word that he introduced. Okay, so any questions about Apollonius before we move on to our next mathematician? Okay, so now we're going to look at a mathematician named Eratosthenes. He was born in a place called Cyrene, but he actually worked in Alexandria. That's actually relevant to the story that we're going to see next. Now, there are two things that he's famous for. So the first thing he's famous for is the measurement of the earth. So here's the story. So during the summer solstice, so that's the day in the year where the sun is the most overhead if you're in the northern hemisphere. So during the summer solstice, the sun shone straight into a deep well at a similarly named place at noon. So the sun is directly overhead on that day. So because the well is very deep, the only way for the sun to reach all the way to the bottom of that well is if the sun is like straight overhead. If it's at a slight angle, the sun won't make it all the way to the bottom. Okay, so Alexandria was on the same meridian, and so 5,000 states north of Cyrene. Okay, so the sun is directly overhead in Cyrene, but it's not directly overhead in Alexandria, where Eratosthenes was. So what he did was he measured the angle. So this is what straight up looks like to Eratosthenes. So basically it's perpendicular to the surface of the earth. That is what straight up looks like. Meanwhile, now here's the thing, the sun is so far away that these lines are effectively parallel. They're not exactly parallel, but you can't, the difference is so small you can't measure them, so they're regarded as being parallel. So basically he's measuring this angle. It's the angle between what he views as straight up versus where the sun is. Now, by the way, this angle in here, because of properties of parallel lines, if you take a parallel lines and then you cut it with a straight line, then corresponding angles are congruent. So that angle is also the same. That'll be relevant. So he measured theta to be 1/50th of a circle. So meaning 1/50th the way around a circle. So in modern terms, we would say that it's 1/50 of one rotation around the circle. So that would be 7.2 degrees. So the total circumference of the Earth is going to be, so this is 1/50th around the Earth. And the length is 500 stades, or rather 5,000 stades. So 1/50th of the way around the Earth is 5,000 stades. So then you have to multiply by 50 to get all the way around the world. So it's 50 times 5,000. So the answer is 25,000 stades. Now, of course, the question we have is, how accurate is that? Well, the thing is, it's going to depend on exactly how big is a stade. And then depending upon the answer to that question, and there's going to be a range of answers, you're going to get between 24,000 to 28,000 miles, or 39,000 to 46,000 kilometers. What's the actual circumference of the Earth? 24,901 miles. So if the stade is on the lower end of the estimate, that is a surprisingly accurate number. And even if the stade is on the larger end, if the actual value is about 25,000 and his estimate is about 29,000, that's still a remarkably accurate estimate, especially given the times. So he did a pretty accurate measurement of the circumference of the Earth using a very clever technique by looking at when the sun is directly overhead in a city, and then compared it to Alexandria. Now, next we have the sieve of Eratosthenes, which is something that you theoretically might have seen this in a class, just because it's kind of an amusing thing. So what it is, it's a method of generating prime numbers. So what's the method? You write numbers in an ordered list, 1, 2, 3, 4, 5, etc. And then you keep going depending upon, how big are the prime numbers you're looking for. Do you want all the prime numbers up to 100? Then you would write the numbers 1 through 100. Do you want all the prime numbers up to 1,000? Well, you'd write the numbers from 1 to 1,000. You begin by crossing off the 1. The reason is that 1 is not prime. Remember, prime numbers are numbers whose only factors are 1 in themselves, like 2, 3, 5, but you exclude 1. The next thing you do is you circle the number 2, because 2 is a prime number. Now, counting by 2s, you cross off every other number. You're basically crossing off all of the multiples of 2 on your list. Next, you circle the next number that is not crossed off. Let's call it n for simplicity. Now we're going to count up by that number in order to cross off all multiples of that number n. And then this little arrow is indicating that you keep repeating the process. Now, when do you stop? So let's figure out when you stop, and then after that, we're going to look at an example of carrying out this process. So let's say you want to find all primes up to a certain number x. Like, for example, I might want to find all primes up to 100. Now, we're going to be crossing off the composite numbers. Those are the numbers that can be factored where neither of the factors is 1 or itself. So 6 is composite because it's 2 times 3. Now, the only way to factor 7 is 7 times 1. You cannot find any other factorization for 7, so 7 must be a prime number. Okay. So each composite number is crossed off when you hit its smallest prime factor. So for example, when do you cross off 100? Well, since 100 is a multiple of 2, when you're crossing off all the multiples of 2, you're going to cross off 100. When are you going to cross off 99? Well, it's not going to be crossed off when you're crossing off multiples of 2 because it's not a multiple of 2. The next prime you're going to find is 3. When you cross off all the multiples of 3, you're going to cross off that 99. So, how big is the smallest prime factor of a number x? And let's see, I wanted to use x, so let's say x is a composite number and can be factored as x is equal to p times q. Of course, you want neither p nor q is 1 when we do this factorization. And let's notice something. If p is greater than the square root of x, then q must be less than the square root of x. Why? Otherwise, if both factors are greater than the square root of x, here's what happens. You have x is equal to p times q. P is greater than the square root of x. Q is greater than the square root of x. Square root of x times the square root of x is x. So you have x is greater than x, which is a contradiction. So if one of these is greater than the square root of x, the other must be less than the square root of x. So just as an example, 36 is 6 times 6. It's also 18 times 2. So 18 is greater than 6, so 2 must be, the other factor must be less than that square root. The bottom line is, if you're trying to find all primes up to x, you can stop when you find a prime that's greater than the square root of x. Now we're ready to look at an example. So we're going to find all primes up to 80. So I'm going to begin by crossing off 1. Then I'm going to circle the 2. And then I'm going to count by twos, and every time I say 2, I'm going to cross it off. So starting with the 2, and now I'm looking at the 3 and then the 4. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And you're just counting up by twos. And in the process, you're crossing off all of the multiples of 2, which means all of the even numbers. All right, I'm going to switch colors. Now, I've finished that step, and I'm going to circle the next number that's not crossed off, and that is 3. Now, starting at 3, I'm going to count 1, 2, 3, and each time I say 3, I'm going to cross off that number, and in that way, I'm going to cross off all multiples of 3. Some of the numbers have already been crossed off, like the first thing that I want to cross off is 6, but since 6 has a smaller prime factor, namely 2, it's already been crossed off. So I need to cross off, let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And in this way, you're going to cross off all multiples of 3. Okay, so now I look to see what is the next number that has not been crossed off, and that's a 5. Therefore, 5 must be a prime number. So I need to now cross off all multiples of 5 by just counting up by 5. If a number's already been crossed off, I'm going to ignore it. So I would go 1, 2, 3, 4, 5. 10's already been crossed off. 1, 2, 3, 4, 5. 15's already been crossed off. 1, 2, 3, 4, 5. 20's already been crossed off. Finally, we get something to cross off. It's 25. And then we're going to cross off 35 and the 55 and the 65, and all the other multiples of 5 have already been crossed off. We circle the next number that's not been crossed off. Now we count up by 7 and cross off all multiples of 7. So 14's already been crossed off, 21's already been crossed off, 28's already been crossed off, 35's already been crossed off, 42's been crossed off. 49, need to cross that off. Okay, continue counting up. 56 has already been crossed off. 63 has already been crossed off. 70's already been crossed off. There we go, 77. Okay. Now we're going to circle the next number we see. That's 11. That's a prime number. But 11 is greater than the square root of 80. So the square root of 80 is less than 9. 11 is greater than the square root of 80. So we stop. And what do we do now? All the numbers that remain are prime numbers. And you can check that all the numbers that remain, when you try to factor them, the only factors you get are 1 and itself. So let me just note that, here we go. I'm going to just jot it down here. All remaining numbers that are not crossed off are primes. Okay, so any questions about the sieve of Eratosthenes before we move on to our next mathematician? Okay, so our next mathematician is Aristarchus of Samos. He lived about 310 to 250 BCE. And he's most famous for his astronomy. Now, he believed in a heliocentric system. So helios is sun. So he believed that the sun is in the center of the universe. Now, one thing that he did that's interesting is he did some calculations regarding the distance to the moon and the sun. Now, what he was not able to do is actually calculate the distance. But he did something else that's just as interesting. So he asked the question, so I know that the sun is further away from the earth than the moon, but how much further away is it? And so that's the question that he's trying to answer. And so he's looking at this picture where, so here's the moon. And so from the point of view of the earth, this is going to be a half moon. And then measuring this angle, it's 87 degrees. Of course, they didn't use degrees. And this is 3 degrees. They had other ways of dealing with it using ratios. So let's let S be the distance from the earth to the sun. X is the distance from the moon to the sun, and M is the distance from the earth to the moon. And the reason why we choose a day where we get a half moon is because this is going to be a right triangle. And so, again, he's using ratios. We're using a more modern notation to look at them. But in effect, here's what he's saying. That the sine of 3 degrees is between 1/20 and 1/18. Now, the sine of 3 degrees is m/s. So that's opposite over adjacent, where this is 3 degrees. So he wouldn't have used the sine notation, but he would have used this ratio instead. And so the bottom line is, if you multiply both sides by s, you get s times the sine of 3 degrees is equal to m. So the distance to the sun times the sine of 3 degrees is m, where the sine of 3 degrees is between this and this. So now taking this equation here and multiply through by s, you get s over 20 is less than s times sine of 3 degrees is less than s over 18. But s times sine 3 is m, so you get s over 20 is less than m is less than s over 18 by substitution. So I've just copied that inequality from the previous page. And looking at the yellow inequality, if you multiply both sides by 18, you get 18m is less than s. Looking at the green inequality, if you multiply both sides by 20, you get that s is less than 20m. Therefore, 18m is less than s is less than 20m. His conclusion: the sun is between 18 and 20 times further from the earth than the moon. Now, the actual value is, the difference in distance isn't a factor of 20, it's a factor of 400. So where did Aristarchus go wrong? Well, his method was actually very good. The problem is, it would have been very difficult at that time to measure this angle accurately. So if he was able to measure the angle more accurately, he would have actually had a more accurate estimate of the difference in distance between the moon and the sun. Now, by the way, Aristarchus also used this to find the relative sizes of the sun and the moon. And so basically, using similar triangles, and so here's a triangle, and you get basically the same relation between the diameter of the moon and the diameter of the sun. And again, it's way off just because of his error in measurement. So this distance versus this distance is going to be a factor of 20. And so therefore, this height to this height will also be a factor of 20. Okay, so next, let's just spend a couple of minutes on Eudoxus. So he was earlier than Euclid, and he's famous for his work on proportions. Now, here's how he viewed it. So let's say you have this proportion. A is to B as C is to D. Of course, in modern terms, we would just say the fraction A divided by B is equal to the fraction C over D. He says this is true if and only if, given any integers m and n, if MA is less than NB, then MC is less than ND. So basically, you're multiplying the first numbers by m. So the first number's A and the first number's C, you multiply them by m, and then you're multiplying the second number by n. And if you get this inequality for the A and the B, you get the same inequality for the C and the D. And then likewise, if when you multiply m times A, it's equal to n times B, then if you multiply m times C, it's equal to n times D. If you multiply m times a and it happens to be greater than n times b, then similarly, m times c will be greater than n times d. Let's look at an example. And I color-coded it so that you could see what's what. So let's just look at it in modern terms using fractions. So 2/3 is equal to 4/6, or the ancients would have said 2 is to 3 as 4 is to 6. Let's say m is equal to 3 and n is equal to 5. So I'm going to multiply m times the first number, and it happens to be less than n times the second number. So since that's true, if you multiply m times 4, it will also be less than n times 6. Let's choose a different m and n. Now, when I choose m equals 3 and n equals 2, I multiply these numbers by 3 and 2, and they happen to be equal. So 3 times 2 is equal to 2 times 3. Therefore, when I do the same multiplication using the 4 and the 6, I'm also going to get equality. Finally, what if I have m is 4 and n is 2? In this case, 4 times 2 is greater than 2 times 3. So therefore, 4 times 4 will be greater than 2 times 6. So whatever equality or inequality you get for the first pair, if you perform the same multiplications, you get the same inequality for the second pair. So that's how he viewed the proportions. Now, he also did the method of exhaustion. So let's look at some of the things that he proved. The first thing is, here's a lemma. Given two magnitudes having a ratio, that really means neither is 0. So it doesn't make sense to talk about a ratio if one of the values is 0. So some multiple of the first exceeds the second. Here's a magnitude m1, here's a magnitude m2. The claim is some multiple of this exceeds that. So here's m2 again. And notice that if I take 5 m1s, that goes further out than m2. So 5 times, and I wrote that wrong. So 5 times m1 is greater than m2. So using numbers, let's say m1 is 3 and m2 is 13. Well, notice that 5 times 3 is 15, and 15 is greater than 13. So 5m1 is greater than m2. Now, this is known today as the Archimedean property. Okay, so now here's something that he proved using the method of exhaustion. Let's say we have the first circle. It has diameter little d and area little a. We also have a second circle, diameter capital D and area capital A. Then the ratio of little a to big A is equal to the ratio of little d squared to big D squared. How did he prove this? He used inscribed and circumscribed polygons, and he increased the number of sides. Doing that, he was able to show that this inequality, little a over big A, is less than little d squared over big D squared. That was false. Similarly, little a over big A is greater than little d squared over big D squared. That one's false too. Since these are both false, both inequalities are false, there's only one thing left. They must be equal. Neither one is less than the other, so they must be equal to each other. By the way, in modern terms, we would say that we're using the trichotomy property. So you might have seen that in other classes. So now the next mathematician that I would like to tell you about is named Diophantus. So this is Diophantus of Alexandria. He lived about 200 to 284 AD. Those dates are approximate. Both of the dates are approximate. He wrote a series of books called Arithmetica. I believe it was 13 books, if I'm not mistaken, and some of them survive. And these books are about solving equations, although remember that, again, they weren't using the kind of algebraic notation that we use today. Now, some of the equations that he solved, today we called Diophantine equations, named after him. So if you are taking a number theory class and you're studying Diophantine equations, these are named after this mathematician Diophantus. So what he was interested in are equations involving whole numbers. Now, we've already seen an example of a Diophantine equation, so let's just look at that. So the example that we've already seen is the example of Pythagorean triples. So those are whole numbers, a, b, and c, satisfying a squared plus b squared equals c squared. And so, for example, 3, 4, 5 would be a solution. 5, 12, 13 would be a solution. So those are whole number solutions to a squared plus b squared equals c squared. Now, it's important to note that there are lots of other solutions, but he was only concerned with what are the whole number solutions. Now, another interesting thing about Diophantus is that he was the first ancient Greek mathematician to actually recognize fractions as numbers. And because of the fact that he wrote a lot about solving equations, It probably was for a very practical reason, but he developed a series of abbreviations of words and phrases that occur a lot when you're talking about solving equations. And so he developed a system of abbreviations to make it easier to write about solving equations. Now, later in this course, we're going to learn about Fermat's last theorem. It's something that you've probably seen before, but he was an inspiration to Fermat. And so Diophantus is an important character in the story of Fermat's last theorem. Now, the next mathematician that I would like to briefly talk about is called Ptolemy. So he lived around 100 to 170 AD. And he wrote a work that's now known as Almagest. This book was very influential. It was copied and used again and again and again over many centuries. So probably second only to Euclid as far as how much influence it had. Now, the word Almagest means the greatest. So here's the Greek word that means greatest, megiste. So just like mega usually means great. So, and then this ending is a superlative ending. And so this means greatest. And so this work is called the greatest. So the question is, where did this al come from? In what language is al the? Does anyone know? Well, it turns out that in Arabic, al means the. And so the reason why it's called Almagest is because of the fact that this is the name given to this work by Arabic mathematicians. And we'll see later what role the Arabic mathematicians played in the story of not only the development of mathematics, but why so many ancient works were preserved until today. So this is a work that is basically about astronomy and planetary motion and that sort of thing. So Ptolemy had a geocentric model of the universe. So in other words, what's at the center of the universe? Geo, meaning Earth. So Earth is at the center of the universe. So he studied planetary motion. And so basically his view is that Earth is fixed, the universe is a sphere, and basically the celestial realm moves in spheres about the Earth. So this work was very influential up until fairly modern times, until it was replaced by the work of Copernicus. And so the last person that I would like to talk about today is Hypatia. So this is Hypatia of Alexandria, Egypt. And this is the most modern person that we are considering when we're talking about the Greeks. So she's one of the earliest known women mathematicians. And there actually were earlier women mathematicians. For example, there were women in among the Pythagoreans. And there's another woman who is an earlier named woman mathematician, but we don't have as much information about what the earlier person actually did. But we do know a lot about what Hypatia did. Now, if you're at all curious to learn more about Hypatia, there's actually a movie about her. It's called Agora. Now, she was a Neoplatonist, so that was her philosophy. She taught philosophy and astronomy. She wrote a commentary on Apollonius, and so that was about the conics, for example, as well as Diophantus, so that was the number theory that we just learned about. Now, by the way, her father was also a mathematician, Theon. Now, she also likely edited the surviving text of Ptolemy's Almagest. So in other words, the version that we know today is what was her version of it, the version that was edited by her. Now, her story actually came to a very sad end because she was murdered in the year 415 by a mob. According to the ancient accounts, it's possibly for being a pagan, and that, and more likely than that is for political reasons. In any case, she was influential at the time. She had a lot of students. This mob and the leader of the mob didn't like what she was teaching, and so the mob murdered her, and so she came to a sad end. Okay, so this is the end of the Greeks that we're going to be talking about. Here and there, we might need to bring up somebody if it's relevant to something that we see later. But in any case, after the exam, we're going to start looking at some of the contributions of other ancient civilizations to mathematics. We're going to look at some ancient Chinese mathematics, some ancient mathematics from India, the Arab mathematicians, etc. And then we're going to eventually look at a few more modern things. Okay, so that's all I have for today. So I'm going to stop the recording now, but I'm going to stay a few minutes in case anybody has any questions.